Hello, this is Concrete Path and fifth lecture for your RCC that we call as DRB doubly reinforced beam DRB. Till now we were studying singly reinforced beam. In that case we were placing the steel only on the tension zone. So we were saying that the external bending moments, factored external bending moments, that they should be less than the limiting moment of resistance of the section. This was the case of the singly reinforced beam. Now for the doubly reinforced beam, we say that we say your dimensions are fixed. Somehow, if your dimensions of B and D is fixed, that means B and D is fixed. Then after that, the bending moments that are applied, external bending moments applied, that they are greater than limiting moment of resistance. The external factored bending moments, that is greater than limiting moment of resistance of the section. At that point, if you want to design it by what you call as singly reinforced beam, if you want to design it by singly reinforced beam, that means your section would be over reinforced. Section is ORS in that case. To overcome that effect, we don't want that section to be ORS. We want section to be URS. And how can we get that URS section if this applied moments are greater than limiting moments? So there's 100% chance that the section would be that over reinforced section if the beam was singly reinforced beam. If the beam was singly reinforced beam, your section would definitely become over reinforced section. Okay, now to overcome this, so your variables of B, D is fixed, so you can't change the dimensions. Now what you can change, the grade of concrete, or you can change the grade of steel. You can change the grade of concrete and grade of steel. So, but since when we design one particular what you call as we want to design a particular beam or a particular what you call as a particular structure, our steel is fixed, our concrete is also fixed, that we want particular strength of M25, M30. So that part is also fixed, and steel grade is also fixed. Then we say there should be one more thing we can do. We should change the content of steel. So AST we can change. So we can work with this what you call as steel. We can change the steel content, area of the steel we can change. So in this case, we say we might provide steel, we might be providing steel greater than AST limiting. We might be providing steel greater than AST limiting. But you might be saying that the structure would become ORS. You might be saying that the structure would become ORS now. Now we say that we don't only increase AST greater than AST limiting, we also add steel in the compression side also, that some amount of steel in the compression also, area of steel in compression zone. So we increase that a part of the steel we are increasing in the tensile zone, is that some value of AST, and some value of steel we are adding in the compression zone. And because of that what's happening? Because of that, our neutral axis does not change. And your moment capacity is that moment resisting capacity of the section gets increased. So it can take now more moments for the same B and D cross section of that B and D. So let's try to get that what we are saying. We are saying that if you want to design a singly reinforced beam, you are applying a bending moment, factored bending moment of MUE that is greater than MU limiting. for the singly reinforced beam. Your B and D is fixed. Your B and D is fixed. Okay. Now, so if you want to design it as a URS for this case, it won't become URS. That means for this case, it would become over-reinforced section because your moments are greater than limiting moments. If it was MUE equals to MU limiting, it was balanced section for the singly reinforced beam. But we say that your moment somehow are greater than external that limiting moment of resistance. So that's why we say we should not go for singly reinforced beam. We should go for DRB. That means what we are going to do now, we are going to have same beam of same dimensions D cross D. And then the steel here we have some ASD. We have some ASD here, and we are going to place some area of steel also from the top side also. ASC. Add some effective depth, that's effective cover D dash. We call it as effective cover for compression steel. D dash is your effective cover for compression steel. Effective cover for compression steel, center to center for compression steel. Okay. Then we say that the stress block, we are going to treat it in two different beams. We say that there is one beam having having the dimensions of same B and D, B cross D, then there is some steel applied here, and that steel, we say this steel is equals to area of steel for limiting condition. For limiting moment of resistance, we said there is some steel placed here. Okay, and then we treat it. We say that for this one we can treat it as a singly reinforced beam. We can treat it as a singly reinforced beam with a stress block of 0.87 Fy ASD limiting. And this was your tensile force, and the stress block is in this fashion up to the neutral axis we have. So we have some C force, C equals to 0.36 FCK B times XU, and the stresses at the top 0.45 FCK. So we want to treat it in this way, and we want to add one more beam that we call as imaginary beam, plus one more beam that's imaginary beam of dimensions B cross D, such that we have some steel placed here. We can call it as AST2, and we have some steel at the top. We can call that area of steel in compression zone. Add some D dash from the top, and for this we say that there is no concrete anywhere. Only the two forces are acting. Some C force is acting here. C force. Let's write it as C2, and that C2 we can calculate. And there's some T force acting here at this cross section. So some T force is acting here. T force of, we know that T force is 0.87 Fy AST2, and there's some lever arm also. And for this one, lever arm is equals to Z2, that is equals to D minus D dash. If the total up to the center to center of those bars is D, small d, and this part is your small D dash, then the lever arm of these two forces centroid of the C2 force and T2 force is equals to D minus D dash lever arm. Okay. So then we can say the moment of resistance of this section, if you are applying any moment, external bending moment of MUE, that has to be resisted by a beam number one having the moment of resistance equals to MU limiting, and second beam is there that can develop a moment of resistance equals to M2, that can develop that moment of resistance equals to M2. So the extra part that was trying to make the singly reinforced beam as a over reinforced section, that extra moment is because of that M2. So let's say that external moment was 180 kilonewton, and your limiting moment of resistance for the singly reinforced beam was 150 kilonewton. That means the extra M2 part was trying to make the beam under over reinforced section. If you want to design it by singly reinforced beam, your beam was trying to become over reinforced section because of that M2 of 30 kilonewton meters. And if I don't want that over reinforced section, I want that design of doubly reinforced section. So that design is in this fashion. So that M2 is to be resisted by some C force, C2 force into some lever arm Z2, or it can be resisted by some T force, T2 force into lever arm Z2. So this is our general what not of this what you call as what and what not for this what you call as doubly reinforced beam. Okay. So one more point is here. We see that the steel is placed at some location D dash from the top. Can you see that? Steel is placed somewhere at the from the top at some location. I would say, can you tell me the strain from the assumptions we have in the limit state of flexure? What was the assumption number 2? Assumption number 2 was that strain at the top most extreme compression fiber is 0.0035 and it goes to 0 at the neutral axis. We say that in the doubly reinforced beam we are not changing the neutral axis. We are keeping the neutral axis as it's. We're keeping the neutral axis as it is. We're keeping the neutral axis as it is. Okay. And one of the assumption was assumption 6, that strain here in the outermost fiber of the tension zone, that is steel, strain in steel should not be lesser than 0.02 plus 0.87 Fy by Es. So then we join those by straight line. Okay. Now at the location of what you call as compression steel, we would say there should be some strain corresponding to this value. There should be some strain associated here, that ESC. We can write that ESC, why that ESC is the strain at the level of compression steel. Strain at the level of compression steel. Can you get that? What is the strain at this level of compression steel by the similar triangles? If this is the location of XU neutral axis is at XU, so I would say we have ESC for the length of XU minus D dash. If this was your D dash, I would say XU minus D dash for this triangle, and your strain of 0.0035 for the triangle of for the depth of XU. So you can get the equation of ESC equals to 0.0035 1 minus D dash by XU. So this is our strain at that particular location. This is the strain at that particular location. Okay. Okay. Now the thing is that we know that how to get the limiting moment of resistance. So we are treating this that doubly reinforced beam as sum of two beams, as sum of two different beams. So we say that doubly reinforced beam can be treated as a sum of two different beams. One of the beam is acts as a singly reinforced beam. So you can write that one of the beam is acting as a singly reinforced beam with some steel provided as area of AST limiting. So we provide the steel equals to AST limiting in the beam 1, and its analysis we know how to get the steel area of the steel for corresponding to a singly reinforced beam. What is the moment of resistance of a singly reinforced beam? That's all we know. We were doing that for 3-4 hours. So we know that this part we know. Okay. And we say that the extra part that is trying to make the singly reinforced beam as a over reinforced section, that moment M2 we can say that is the delta M. So that moment 2 we can also call it as difference of those moments. This difference of moments is the external factored moment minus limiting moment of resistance of singly reinforced beam. And this is applied on the section. And this M2 has to be balanced by that imaginary beam of M2. Beam 2. Let's write it as B2. So this beam B2 has to resist this what you call as this delta change in difference of those moments. So I would say this difference of those moments, delta M has to be resisted by some force of C2 and some lever arm of Z2, and similarly that is to be resisted by some T2 force and some Z2 lever arm. Okay, now we can get those. You already can get that we are adding some steel at the bottom, some AST2. We can write that 0.87 Fy AST2. So you can get the value of what should be the amount of steel required for that extra part of that moment delta M. So that part is easy. So AS2 is easy to get. That is easy to get. AST2. So when we talk about doubly reinforced beam, what you have to design in the doubly reinforced beam? What you have to design? What you have to design? Your dimensions are fixed. BD is fixed. You can't change those. Only what you can do, you need to get the value of ASC. You need to get the value of AST limiting plus AST2. That is total AST you need to get. So that's all the job that you need to perform for the doubly reinforced beam. So one is your ASC and one is your AST2. AST, that's sum of AST limiting plus AST2. So there are two different values we need to get for the design of doubly reinforced beam. So one of the parts we can get, that's very easy to get. Is it easy? I think it's very easy. It's very easy to solve AST2. Now talking about that C2, this C2 is this is the C2 force that is because of some stress in steel at the compression in the compression zone, the steel in the compression zone. This is the stress. Let's write that stress in compression steel at the rate of strain, at the level of strain equals to ESC. And similarly, we say that what is the value of C2? We say already have accounted that at this location there is some force of FC. We call it as FCC, and that FCC is the what you call stresses in concrete at the compression where we have placed that steel compression steel. FCC is what FCC is. So FCC is that stresses in concrete at the level of compression steel, at the level of compression steel. So that means at the level of ESC. So we already have that concrete effect here. Then we subtracted the effect of that in this part ASC. So we write that your C2 force is actually some FSC minus FCC times the area of the compression steel. So this is your C2 force. This C2 force is that summation, that FSC stress in steel, compression steel, minus stresses in concrete at that same level, and the area of that steel, compression steel total. You might be saying that what should be those values of FCC and what should be that value of FSC. Let's talk about what should be the value of FCC. What should be the value of FCC we are going to take? What should be the value of FCC we are going to take? We say that that steel is costlier. You already know steel is costlier. We want to place that compression steel closer to the extreme fibers. We want to place it closer to the extreme fibers. It should be closer to the extreme fibers such that strain ESC is more. If the strain ESC is more, that means your stresses in that steel is also more. Can we say that? Stresses in steel is also more. Okay, from that perspective, I would say you should place those steel bars in compression zone somewhere to the top side. It should be very close to the top side at some effective depth of D dash, at some effective cover of D dash. So, but thing is that if you talk about that singly reinforced beam, we know that the stress block is rectangular up to a point. After that there is parabolic variation. And if this is neutral axis of XU, and we know that this top part was equals to 3/7 of XU, and bottom part is 4/7 of XU, and we would say that stresses stresses at the top up to the level of 3 by 7 of XU, that is a constant value of 0.45 FCK. Now you would be saying, what should be the value of FCC? We usually place those bars in that 3 by 7 part. We usually place that steel in that part, that 3 by 7 of that XU. We usually place that steel area compression steel in that region somewhere here. So the FCC should be equals to 0.45 FCK. It should be equals to 0.45 FCK. And we for the practical use, we say that practically what the value of, if you talk about practical values of d dash by d, that d dash by d is somewhat in the range 0.05 to 0.2. So there is some effective cover, let's say there's some effective cover of 50 and there's some effective depth of 500, so 0.1 is there a general sum value of 0.1. So we say that there's some effective depth, there's some effective depth of d dash, there's some effective depth of d. Then we say that what is the ratio of d dash by d, what is the ratio of d dash by d, and from that we say that the general value of that d dash by d is somewhat in this range. So this is our practical range of that ratio d dash by d, and based on that we are going to take we are going to use those different kinds of steel, and we want to see what is the strain, and correspondingly we want to see where our steel bars has to be placed. Let's analyze this. I would say if you take that strain in compression steel is 0.0035 1 minus x dash by d dash by xu. Okay. One more thing is that we want to see what should be the value of FCC we are going to take. Value of FCC, we know that concrete stresses in concrete is maximum, we have 0.45 FCK, and then it decreases to 0 at the neutral axis. Do we know that? And this value was equals to XU. And this part, this is 3 by 7 of XU. Now, we usually say that your d dash by d is in the range 0.05 to 0.2. Okay. Now, let's say this this part we are doing to know what should be the value of FCC. This, you can write this in this way, that what should be the value of FCC. For that, we are doing this all this stuff. We are doing all this stuff. Let's talk about what you call as mild steel, Fe250. I would say, if you say what is the d dash by d, what is the value of d dash by d? What should be the value of d dash by d? Equals to, I would say, let's have a critical value. Let's have a critical value that d dash is somewhere here. Let's say that d dash is equals to 3 by 7 of XU. 3 by 7 of XU. Okay, 3 by 7 of XU. And to get the critical limit, we are taking now here we are taking XU limiting. We are taking here XU limiting. So if I write that XU limiting, if I talk about XU limiting now, limiting condition, so I would say if the value of d dash is equals to 3 by 7 of XU limiting, and I know the value of XU limiting for mild steel, I would say 3 by 7, and that is 0.53, and that multiple of d also. So I would get a ratio of d dash by d equals to 0.2271. Okay, that means even on the ratio of 0. Up to the ratio of 0.2271, we say that your stress in concrete would be 0.45 FCK. This is our general theme here. Based on this, we say if the d dash is going up to the level of 3 by 7 of XU, 3 by 7 of XU limiting, at that location we have that the ratio equals to 0.2271. And our general practical value of d dash by d is in this range. That's greater than this value 0.2. That's greater than 0.2. And based on that, we would say we are going to take FCC as equals to 0.45 FCK. And if you talk about FE415, and you apply those again, that critical limit, that you want to go up to the value of d dash equals to 3 by 7 of XU limiting. So your d dash by d has come to equals to 0.2057. Similarly, if you go for what you call as FE500, you would go to some d dash value, critical value of 3 by 7 of 0.46 d. So that d dash by d is somewhere in the range 0.1971. And we say that up to the value of d dash by d, then we generalize that up to the value of d dash by d. So up to the value of d dash by d, we say your FCK, up to the value of d dash by d equals to 0.2. Based on these values, we say that we can have a general view that up to this value we can have for all grades of steel, we can write for all grades of steel, your FCC is that equals to 0.45 FCK. So this was all about that. Conclusion is that you would always take that FCC equals to 0.45 FCK, because your general practical use of d dash by d is always in this range, 0.05 to 0.2. And we say that up to this value of 0.2 ratio, for all grades of steel, you have FCC equals to 0.45 FCK. And one more thing is that even the code is going to ignore, IS code ignores this value of FCC also, but still we calculate it, to get a better understanding of the concepts. We still calculate that. But when we know that what's the value of C2 force, where was that C2 force? We write that C2 force was equals to FSC minus FCC times ASC. We write that. Okay. Now the code says you can ignore even this FCC also, because your stress in compression steel may be somewhat in the range 300 to 400 megapascals, and this would be some value of 5 FCK. Let's say M20 was there, so this is some 9 value. So we can ignore this part as per IS code. But for calculations, we are not going to ignore that. But you can write that IS code ignores that part. IS code ignores this part. Yeah. But still but still we calculate. We calculate that. Okay. So final crux is that FCC is equals to 0.45 FCK. Now we are going to talk about what should be the value of FSC. So we are only left with that FSC. What should be the value of FSC? So one thing is that once your ratio is fixed, you want that effective cover is some value of 50 mm. You would say my compression steel would be somewhere here, but I don't know the value of ASC. I would say they are located at D dash from the top, and there's some effective depth of D. Okay, then once this ratio is fixed, D dash by D for this problem, for this section, okay, then we can say, based on this one, we can say what should be the strain at the level of compression steel. We have the equation ESC equals to 0.0035 1 minus, we talk about like limiting, so d dash by xu limiting. So this is our equation for the strain at the level of compression steel. And we know that if there is strain in compression steel and it's in the compression, so we would say your steel is in compression. Once you have a particular steel grade, and you might have earlier performed that test of stress versus strain of that same material under compression. Obviously, if your material is M415, Fe415, you would have already performed that test. That's available in the codes. You would have performed that compression test of steel, compression test of steel, compression steel test. So we can have some relation of stress versus strain, stress versus strain. So you can write FSC versus ESC, strain versus stress. So there would be some relation. There would be some relation at particular location of value of ESC. You would get some stress in the steel FSC, and that we have in the tabular form, that if you have particular FSC and we have particular strain, then we can add particular value of strain. What should be the value of FSC we have to take? Okay, that's the task we have to do. That's the task we have to perform. That's the task we have to perform. Let's try that. For the calculation of FSC, how do we arrive to this value of FSC in doubly reinforced beam? Let's write that topic. We would say stress in compression steel, stress in compression steel, stress in compression steel. That's FSC in doubly reinforced beam. In the doubly reinforced beam. In the doubly reinforced beam. Okay. Then we say we have different grades of steel. Let's say your Fy is 250 megapascals, your Fy is 415 megapascals, your Fy is 500 megapascals. You can have also 550 megapascal also. Okay, we have different grades of steel, and corresponding to different grades of steel, we have different ratios of what you call as d dash by d, d dash by d, this ratio. And we say that the practical range of that d dash by d is in the range 0.05 to 0.2, and if you have that multiples of 5, I would say 0.1 and 0.15. So we have 4 different values, and these are our practical range of that d dash by d. And we say that stresses in steel, in the mild steel, we say your stresses FSC is 0.87 into Fy. You would calculate that comes to be equals to 217.5. And we say for all values of this, for all values of that d dash by d, your stress in compression steel, if you are using a grade of mild steel, you would always have this value of 217.5 megapascals. So for all values of that, what you call as d dash by d, your stresses in compression steel for mild steel, that's always same. But for what you call as high yield strength bars, we have a different values. So it's a function of that ratio. So let's have the different values. So the starting is from 355.1, and for this one we have 423.9, 458, 351.9, 342.4, 329.2, 329.2, and we have 411.3, 441, 395.1, 419. We have 370.3, 380 megapascals. 380 megapascals. Okay. So for different d by d ratios, these are your FSC values. So if I say what is the ratio if I am using mild steel in the compression zone, mild steel, if I am using Fe415, and the ratio of d dash by d was coming to be 0.15, I would say that FSC in the steel would be this one. This is corresponding to some strain value ESC, and from the curve of stress strain curve of my that Fe415, I got that FSC at that level equals to 342.4 megapascals. Now, what does it indicate? What does it indicate? Why for mild steel we say this is always fixed to 17.5? Let's try to get that value. Let's try to get that value. Once we have that stress strain curve for the mild steel, we have this variation. Okay. We have this variation, and when we plot that stress strain curve for the mild steel, we say we say that for stress value of for strain value of 0. What you call as 0.00109, even for this strain value of 0.00109, your mild steel has started to yield. Mild steel has started to yield. Even on this strain, mild steel has started to yield. So that strain value is almost how much percent? 0.1%. 0.00109 into 100. That's 0.1%. That means on 0.1% of the strain, on 0.1% of the strain, and on this value, your mild steel has been started to yield. Because we are talking about design stress, so 0.87 Fy. So we are not going to fully to the value of Fy. We are going to the value of 0.87 Fy. We would say there is some 0.87 Fy because we are applying that factor of safety, and there is some value of 0.87 Fy somewhere, such that at that location your strain is even 0.00109. But if you take this ratio, any of these ratio, if you take any ratio, let's take the ratio of 0.2. Let's take this ratio 0.2. If you take this ratio of d 0.2 also, I would say what should be the strain in steel? That equation we know, 0.0035 1 minus d dash by XU limiting. And the value of XU limiting we know for the mild steel 0.53 d. And if we substitute that value of d dash by d, d dash by d, d dash by d. So for the maximum, even for the minimum value of strain in compression steel, even for the minimum compression of compression steel, even for the minimum strain of compression steel for a mild steel case, your strain is always coming out to be equals to 0.00218 for this case at the ratio of 0.2. That means when you take the maximum ratio, even on that maximum ratio, your strain in steel has reached to this value. But if you compare this strain in the concrete in the steel 0.00218, that is very bigger value than as compared to this one. So your ESC 0.00218, that is greater than 0.00109. So that means even on this value your mild steel has reached to the yield stress of 0.87 Fy. And at this location it has already gone a lot of that deformations. It has already gone that lot of deformations has been occurred. Deformations already occurred. Okay. Let's take any general value now. Let's talk about a particular value. I would say for the d dash value of d dash by d value of 0.005, and I am going to study that Fe415. I want to talk about Fe415, how I get this FSC. So I would say at this value of what you call as ratio of d dash by d equals to 0.005, I want to say what is the strain in the compression steel if I am using that Fe415. What is the strain at that location in the steel? So I would say that value is equals to 0.0035 1 minus d dash by XU limiting, and value of XU limiting is equals to, what is the XU limiting equals to for the Fe415? 0.48 d. And when you substitute the value of d dash by d, d dash by d equals to 0.005, you would get the strain in steel coming to be equals to 0.003135. 0.003135. That means now we already know the stress strain curve for the what you call as Fe415 for compression test. Then for particular value of strain, somewhere is equals to 0.003135. You have already plotted that and made some sort of table that's provided in the table code also. So you would say what is the stress in the steel at that strain value. So that's how we calculate that stress FSC. But we directly have provided you tables, so you can check the values of that FSC at different values of strains and at different values of d dash by d directly. So and one general, if you're not using the code, you can have a general perspective of that what's going here. If you talk about now if you finalize it, if I say what should be the value of FSC for mild steel? What should be the value of FSC for mild steel? I would say that is equals to 217.5 megapascals. That's always equals to 0.87 FY. So this is the one of the values we can have without using the code. And if I calculate what is the value of 0.87 FY for all those all these, I would get some values. I would get some values 0.87 FY into 415. What is this value coming out to be? 361.05, and this value is equals to 500 times that, 435 megapascals. 435 megapascals. We say that this value is not already, this value we don't achieve. This value we don't achieve properly. This value, because your HYSD bars do not properly yield in the compression zone, so we don't take that maximum value. So it depends on the ratio of D dash by D, and accordingly we can get the different ratio of that, different values of FSC. So if you see that this 361, if you compare this 361, do you see with here what's the maximum value we can have? 355.1, and it goes decreasing. It is decreasing as the ratio increases. So one conclusion is that your D dash by D increases, D dash by D increases, and your FSC decreases. Now you can have general view that your range for that FSC for my FE415 is going from 355 to 329. So a difference of what you have, 55 minus 29, that's 25. A difference of 25 is there only for the range of 0.005 to 0.2 strain. 0.05. So for this value, for this ratio of D dash by D in this range, your difference is only in this particular range of that stress. So you would say it should have been 0.87 FY. That is 361. It should have been 361, but its maximum value is starting from 355. Then after that, it would be somewhere to a minimum value of 329. That means in the two different intermediate values, we would be having some value, some 340 and some 348, some value around that in those four different peaks values of 0.05, 0.1, 0.15, 0.02. And similarly for the FE500, let's talk about FE500. I would say your 0.87 FY is coming out to be 435 megapascals, but your stress is not properly attained. That peak is not attained. 435 is not attained, but a value of but a value here we have 423. Yeah, 423 is there. You would see 423 is there, 411 is there, 395 is there, 370, and I would say that difference here is difference 370 minus 423. That's a difference of 50. So if difference of 53 is there, a difference of 53 is there for mild steel. So starting from some 325, some 325 is there. Is 423, sorry. Some value of 423 is there. After that, it goes to a minimum value of 370. 370, yeah. It goes to some value of 370. And intermediate values would be somewhere, assuming that linear variation, I would say 423. This would be, difference is 50. So I would say this is some value of 408. This would be some value of 385. 408, 385. So around that you can guess. You can have a guess value also for that. But if you are using directly the code, you can have that perspective also. So the crux is that now the concern was that to get the value of FCC. So FCC was equals to 0.45 FCK that we have concluded for that practical value of D dash by D in the particular range, and FCC was coming out to be in this range. And for the value of FSC, that was a function of D dash by D, and we have different ratios of that, different values for that FSC. And for the mild steel, this is always constant of 0.87 FY. Okay, let's get to the Design of DRB. Let's go to the design of DRB now. Let's go to the design of DRB now. Let's go to the design of DRB. Let's go to the design of DRB. Let's say that this was your section of B cross D, that effective depth of B cross D, and there's some steel here AST, and you are applied a bending moment, factored bending moment of MU external. Okay, and we are providing some steel also from the top at some effective cover of D dash. Okay, and this one is your D that effective depth up to the tensile reinforcement from the top. Okay, now we say that we can equate it in terms of two beams, in terms of two beams, in terms of two beams, in terms of two beam. One of the beam looks like in this way, and one of the beam looks like in this way. So one of the beam looks like an imaginary beam, and for this one we say it is having a resistance, moment of resistance equals to mu limiting. It's giving you a moment of resistance equals to limiting moment of resistance, and this one is going to resist a moment of mu2. It's going to resist a moment of mu2. Okay, now we will say that this is similar to that of singly reinforced beam. This is what you call as, this is similar to that of a singly reinforced beam with some steel provided here equals to AST limiting, and we have some neutral axis. Same neutral axis we have at the same level. We have neutral axis at the same level, so you can have neutral. You can write the neutral axis at the same level. XU is at the same level for all those, same level. For actual beam, for your actual beam A, and for your beam number 1 and beam number 1, XU is same, because we are adding that we are adding the neutral, we are adding the steel in such a way from the top and bottom such that your neutral axis remains same. Okay, then after that we have one more beam, that's imaginary beam, and it's having some steel at the top, that is ASC, and it's having some steel of AST2 at the bottom. Okay, then finally we say that the total moment you are applying on the beam, moment you are applying on the beam, external moment, that should be resisted by beam number 1. That would provide you, or that would give you resistance of mu limiting, and plus the moment resisted by beam number 2. Beam, there is no beam actually in beam number 2, but the steel is provided at a particular location from the neutral axis, a part of that steel in the compression zone and part of that in the tensile zone, such that it would deliver you a resisting moment of mu2, and that mu2 is the difference of external minus limiting moment of resistance, so that we can write mu2. Okay, so why you can write that mu limiting is that this is limiting moment of resistance of singly reinforced beam, and this is your moment resisted by imaginary beam, m resisted by imaginary beam, you can write imaginary beam. So I would say some of the steel, we say that there is some steel AST, total steel is AST, we are using some steel AST total, and that AST, total AST we are providing in the actual doubly reinforced beam, that is sum of AST, that's sum of AST limiting plus some AST2, Okay, now from the force equilibrium, I would say from the internal couple also, we can say by the internal couple method also, there's some T force and there's some C force, and C force was we know that C force was some stress in steel minus some stresses in concrete at the same level of compression steel and the area of that compression steel. So this is your C force, and similarly your T force was 0.87 Fy AST1, what do you have, AST2. So they are separated by some lever arm. We already saw what was that value. If this is D dash and this total up to the level here is D, I would say the lever arm is centroid up to the centroidal distance of those C and T forces, that Z is equals to D minus D dash. d minus d dash. So your moment 2, we can solve that moment 2. Can you solve that moment 2? What should be the value of moment 2? I would say that your moment 2 should be equals to FSC minus FCC into ASC, or that's also equals to 0.87 Fy AST2. So finally you would say, what can you get the value of AST2? Can you get the value of AST2? What should be the area of the steel provided for the imaginary beam? And that would be equals to mu2 by FSC minus FCC into ASC, and we have this factor of 0.87 also there. Is it correct? Is it correct? Yeah, it's not correct. It's not correct. You were talking about tensile steels. Tensile steel. So AST2, then we have 0.87 Fy. So this is one of the equation for getting the AST2. And for getting the ASC, we can write that mu2 divided by FSC minus FCC. This is the equation for getting the area of the steel in the compression zone, ASC. Now what is the value of mu2? Can you get the value of mu2? So I would say that mu2 is the difference of the two. mu2 is equals to mu external minus mu limiting for the singly reinforced beam. So once you got the mu2 from these calculations, so after that you can say that mu2 is equals to difference of the two. After that you can get ASC and you can get AST2. Now what about AST1, limiting? That's easy. That's easy. I would say AST limiting is easy. Can you get the AST limiting? Corresponding to a beam corresponding to a singly reinforced beam by equating compression equals to tension. I would say 0.36 FCK B times XU limiting is equals to 0.87 Fy AST limiting. You can get the AST limiting here. So this was the design of our singly doubly reinforced beam. You need only get the that steel AST total, and you also need to get that ASC. So this is all the design of that doubly reinforced beam. Let's take a problem that let's take a problem 1. Let's take the problem 1 we can have from the doubly reinforced beam. That first problem for this doubly reinforced beam we can take